Next, we're going to take a look at pressure and force. So pressure, hydrostatic pressure, is basically a force exerted by a fluid per unit area. So if you think of a gas or a liquid, you can measure its pressure, which is basically the force that it's exerted to expand on all sides. So for example, if you have a box and you have some sort of gas in the box, the gas is actually exerting a force on each of the walls of the box, right? Because at any given point, there's basically an outward tendency for the gas or the liquid to want to expand, and then that's held in place with other particles of the fluid or some sort of wall. So basically, if you have, if you're underwater, the pressure increases, right? So as you get deeper and deeper, the water, the force of the water is exerting on you, on your body, becomes stronger and stronger. So it's basically a pressure. So pressure, what it technically is basically a force per unit area. Per unit area. So basically, it's how much force the fluid is exerting on something per unit area, which makes sense because if I had some sort of plate, let's say this was a wall in a chamber of compressed gas. Well, the gas is going to be exerting a force on this wall. So at a fixed pressure, you get a given force on this wall. Now, if this wall was twice the size and length, the force exerted on the wall would be twice as much with the same pressure. So the same pressure basically tells you how much force is being exerted per unit area. So basically, when you have a fluid in a container, it's going to exert this outward force on the container walls, which is the pressure times the area of the walls. So pressure is measured in a units called pascals. So 1 pascal is equal to 1 Newton per meter squared. So it's newtons per square meter, which has its own unit, pascals. Oftentimes we use kilopascals, where 1 kilopascal is, of course, equal to 1,000 pascals. So atmospheric pressure at sea level, so the standard value is 101.3 kilopascals. So typically when you're just feeling the ordinary atmosphere acting on you, you're looking at 101.3 kilopascals. Of course, this varies, it goes up and down and fluctuates, but this is kind of the accepted engineering average, where if you're going to use sea level pressure, you're going to say it's 101.3 kilopascals. Okay, so if we look at just a box of gas, let's say it is 2 meter by 2 meter by 2 meter, and we have a pressurized gas that has a pressure of, let's say, 500 kilopascals. So about 5 times the pressure of the atmosphere, so it's pretty pressurized. So what's the total, what's the force exerted on, let's just say, one face of the box? So what's the total force exerted on a side of the box? Okay, well, if we just look at that side plate, we have 2 meters and 2 meters, and the pressure is a constant, it's 500,000 pascals. So we multiply 500,000 pascals times 4 meters squared, and we get 2 million pascals, right? So this is newtons, 2 million newtons. So basically 2 meganewtons of force acting on that wall. Now, that's with a box of gas. The real focus of these problems is going to be liquid. So liquid also has pressure, and it applies a force. And we need to know the basic relationship for what the pressure is at a given depth. Because unlike a gas, which can be in equilibrium and therefore have the same pressure throughout the box, the pressure of liquid varies with its depth. So if you have some sort of body of water, so here's the surface, here we're underwater, and you have a depth of x, what's the pressure at a depth of x? Well, the pressure formula that we'll use is rho gx. So rho is the density of the liquid, g is acceleration due to gravity, and then x is your depth. So a few things to note on this. One, let's check out the units. Rho would be kilograms per cubic meter, gravitational acceleration meters per second squared, depth in meters. We have meters times meters over meters cubed, so it's kilograms per meter second squared, which is the same thing as kilograms meters per second squared per meter squared, which is the same thing as 1 Newton per meter squared, because we have newtons right here divided by meters squared. So this does have units of pascals, so that the units check out. The second thing to note is that this technically is only the gauge pressure. Now this is what we use in all of our computations, but it should be noted that this is not the absolute pressure at this depth. This is a measure of the difference between the pressure at this depth and the atmospheric pressure. So it's really a pressure differential between the pressure at that depth and atmospheric. Now this makes sense because when x is equal to 0, this says there's 0 pressure. Now at the very surface level between the water and atmosphere, you're in equilibrium. So at the surface level, the pressure at this water, the absolute pressure of the water and the absolute pressure of the atmosphere should equal each other. So it's only the gauge pressure that's equal to 0 when you're at the surface level. So 0 pressure at the surface doesn't mean that there's 0 absolute pressure. It just means there's 0 increase of pressure from going from the atmosphere to being underwater. And then as you increase in depth, the pressure increases from there. So when you measure the pressure in your tires of your car, you're measuring gauge pressure. It's just picking up on the difference between the pressure in the tire and the pressure of the atmosphere. So this is interesting. When we go diving, how quickly does the pressure increase? Well, let's take a look. Well, rho for water is 1,000 kilograms per cubic meter. G is 9.8 meters per second squared. So just order of magnitude, rho G is about 10,000, let's see, kilogram meters per second squared is newtons, so basically pascals per meter, right? Because this whole thing has to have units of pascals, so when we multiply this by x, we get pascals, so this is going to be pascals per meter. And when you multiply these units together, that works out as pascals per meter. So approximately 10,000 pascals per meter, meaning that every meter increase in your depth, your pressure, or the pressure of the water acting on you, will increase by 10 kilopascals. So every time you go down 1 meter in depth, it's a plus 10 kilopascal increase of pressure. Now, since standard atmosphere is 100 kilopascals, that means each meter dive in depth, you're gaining approximately 1/10 of the atmosphere. So when you go down 10 meters at a depth of 10 meters, you have a pressure of approximately 100 kilopascals. So it's basically twice, so that's the increase in pressure. So you're starting off with 100 kilopascals, and then we're increasing pressure by an additional 100. So when you're at a depth of 10 meters, you're going to feel twice the pressure that you feel just on the surface. And when you're at a depth of 20 meters, you'll feel 3 times the pressure, because the gauge pressure at this depth will be 200 kilopascals, which is plus the pressure that you start off with at the surface. So that gives you an absolute pressure of 300 kilopascals, which means the pressure is 3 times intense as a depth of 20 meters as it is on the surface. So pressure actually increases fairly quickly with depth as you dive. Now the thing that we'll look at an example of doing calculation with all this in the next. This is just an introduction to what all this means. So the thing that we'll keep in mind is that when we have some sort of plate, so let's say we have some sort of dam. So we have water on the other side and we have a plate. We're trying to compute the total hydrostatic force, or the net hydrostatic force acting on the plate. So the pressure is acting on this plate trying to push this plate, and of course you have to hold the plate in place. So this is a very important problem in civil engineering where you might be building a dam or some sort of container that's supposed to hold a large quantity of liquid, and you have to figure out, well, how much structural support do we need so that the liquid doesn't bust through the wall? So the thing that we have to do is that since pressure increases with depth, we take as our slices little horizontal strips. So everywhere on this little strip, the pressure is approximately the same. So we take L of x, so L of x is just the length across of the strip. The strip has height delta x. So the little area of this strip is going to be L of x times delta x. Let's say this is x is equal to 0 and x is equal to h. So the total area is going to be the integral from 0 to h of L of x dx. If you have a constant length across L, you just get the integral of L dx, which is L times h, which is the area of a rectangle. Now the pressure is going to vary with depth, so you have a pressure at depth x. So the total force acting on this strip, I'll call it delta F, is going to be L of x, P of x, delta x. L of x and the delta x form the area of this strip. And the whole thing is that pressure is varying with depth. So everywhere on this horizontal slice, the pressure should be constant because everything's at the exact same depth. So if you're at the same depth, you're going to be at the same pressure level. So you just take the pressure at that depth, so you evaluate P of x, multiply by the area, which is given by the length across, which might also depend on x, times delta x, which is the area of this little rectangle. So the total hydrostatic force is going to be an integral from 0 to h of L of x, P of x, and dx. So this is kind of like the general formula. The last thing to note is that there could be problems where you have some sort of plate that starts at a distance d. And for whatever reason, it might be advantageous to have your coordinates start at the top of your plate and not at the surface level. Well, we're going to have to correct for the pressure formulas because the pressure is not just, we don't just blindly say the pressure is rho g x. Because what if x starts at, a depth of d or some depth below the surface, right? It's only rho g x if x is measured from the surface level. If x is not measured from the surface level, it's going to be rho times g times the depth. So in this case, it's rho g x plus d, right? Because we start off with depth d, and then we add to that a depth of x. So the total depth below the surface of the water is x plus d. If we had something like this, where we had a plate and we're measuring upward like that, x, and this portion here is at a depth d, the pressure is going to be rho g d minus x. Because now x is being measured upward from this depth. So if this is depth d, and then we're going up x, we're now at depth d minus x. So you have to draw the picture and write down what makes sense. There's not just it's always this formula or that formula. Draw a picture and understand what the problem looks like and write down your equations based on the picture for the given problem at hand.